I'm going to explain polar bonds. What a polar bond is an unsymmetrical distribution of electrons. What it's based on is electronegativity. For example, fluorine has the highest electronegativity. Electronegativity is a measurement of an atom's pull for electrons. 4 is the highest number. Francium, being a metal, has the lowest. And francium's value is 0.7 or thereabouts. This makes perfect sense because fluorine is a nonmetal and it wants electrons to fill up its octet. Whereas francium is a metal and it's going to want to give up electrons, so probably the last thing it wants to do is pull electrons. Well, based on this electronegativity table, I'm going to look at a series of bonds. One bond between hydrogen and oxygen, another bond between calcium and nitrogen, another bond between phosphorus and chlorine, and I'll look at another one between, well, that's enough to do. Now what I'm going to base this off of is a table that looks at the differences in electronegativity. The table works like this. If the difference is between 0 and 0.4, that bond is considered to be nonpolar. If the difference is 0.4 to 1, it's considered to be a polar bond. If it's 1 to 2, it's considered to be very polar. And if it's greater than or equal to 2, it's considered to be ionic. So at this point, what I would do is I would go and look at the my periodic table handout and find the periodic table electronegativities for these elements. What I do is I'd look up hydrogen. Hydrogen's given as 2.1. Oxygen is given as 3.4. Actually 3.44. When I get the difference of that, okay, 3.44 minus 2.1, I'm going to get something on the order of 1.34. 1.34 tells me that this particular bond is going to be very polar. So if I were to orient the polarity of this bond, it would be directed towards the oxygen, which has the higher electronegativity, thereby making the hydrogen side hydrogen the positive side. Another way to make this representation is with small sigmas. I'd have a negative to there, and I'd have a positive on this side. So that's where the dipole moment, the polar moment, is coming from. Now looking at calcium, if I go back to calcium, I look on my chart, calcium has a value of 1. Nitrogen has a value of 3.04. Now the difference between these two is going to end up being 2.04. Well, 2.04 turns out to be an ionic bond. And that's exactly what you would expect because calcium and nitrogen form an ionic compound. Okay, oops. Get rid of that. All right. Now looking at phosphorus. Phosphorus has electronegativity according to the chart of 2.19. Chlorine is 3.16. So if I go 3.16 minus 2.19, okay, I'm going to end up with 15, 7, 11, no, 10. That's going to be 0.97. This 0.97 right there, difference, okay, 0.97 means that is going to be a polar bond. So in this case, if I were to draw the dipole moment, it would again go towards the chlorine because the chlorine has the highest electronegativity. So that's the one that is going to be the negative. Phosphorus then becomes the positive side, and I end up with that dipole.